Now, in section 3 of chapter 5, we're going to look at our first real algebraic experience of solving equations. Now, traditionally, when I would teach this lesson, I would set something up like this. And as you can see here, it seems to be like a balance board or scales of something, where what is on this side is the same as what is on that side. And of course, in mathematics, we put an equal sign here. And we say that this side equals this side. And it balances. Now, our purpose in math is to carefully take things from one side Now, this wouldn't balance, but if we took the very same thing from the other side, this would still balance. And going on, taking, let's say, this from this side, that wouldn't balance anymore, but taking that very same thing from the other side. The key throughout solving equations is what you do to one side, you do the very same thing to the other side, until finally, when you're finished, you end up with, let's say, a letter X on this side, a 1X, and then this is equal, let's say, to a 3. So you keep removing things from both sides, or adding things to both sides, or dividing both sides by something, multiplying both sides by something in an equal way, until finally you've isolated a single 1x, and that equals a number. Now when you get to that point, we say you have solved that equation. And that's where we're going here. So, the formula x plus b equals c is the major formula for what we call linear equations. And we'll get into that too as we move on here. X plus b equals c. And another form of this is ax equals c. And we also want to define what is a linear equation, and to check whether a particular value is a solution of an equation. And we've done things like that before. Substituting a value for x, does it make the statement true? All right, let's go on. So once again, this is standard form for the linear equation. It's called linear here because our x is only to the first power. That is, there's an exponent of 1. Now, once the value you're solving for is squared or cubed, they're not linear equations anymore. So, we want to determine whether we have a possible solution. So here we're saying x is a -7. Well, you put a -7 where the x is. We've done some like this before. And then we end up with, on this side, a -2 equals a -2. So this statement is true, and -7 is a solution for this particular equation. How about this? Well, for z, we substitute a -1.1. When we do it, we realize we get a 0.3 on one side and a 0.5 on the other. So this is not true. And a -1.1 is not a solution for this equation. And we're just doing what they call substitution here. How about a 2.7 is y? Well, we put a 2.7 for y. We do the solution. And when we do the subtraction, we get that this side becomes 2.7, I'm sorry, 2.9, and this side is 2.9. So 2.7 is a solution. And I'm going through these somewhat quickly because we've done things like this before. Now, how about this? Is negative 10 here as a value for z? Remember, it comes out as a positive 10. Remember, the absolute value of anything is always its positive value. So this becomes 10 minus 14. This on this side would be a negative 4. And that does not equal a negative 3. So a negative 10 here would not be a solution. And often they remind us that when you are putting values into an original equation, use parentheses around that value. That helps preserve the signs of what you're working with. Okay, we're going to look at various principles in solving equality. Now, the idea is if you have side A equals side B, if you add a C to the left and add a C to the right, it's not the same equation anymore, but it's equivalent. That is, they still will balance. And that's what we're going to be doing here. Now, there are a series of steps we take. We want to get rid of fractions usually. We want to get rid of grouping symbols. We want to combine like terms. And then we want to isolate all the letters on one side, all the numbers on the other. And then we want to isolate the letter so that it's just a 1x or a 1a. And then on the other side equals some value. Those steps that we do are referred to as solving an equation, and they're outlined here. So, now the text is going to show you one way to do this. I'm going to also suggest another way. Now you want to isolate the x here. So what do we have to add to a negative 3 to have it become 0? Well, we're going to add its additive inverse, which is plus 3. Now I did something to one side. I must do the same to the other side. So here, this adds up to a 0. I'm left with an x on that side. And now this side becomes 10. And if I put the 10 as the x, 10 minus 3 is 7, and it checks. Now, our text is going to suggest the horizontal method, which is good as well, and we'll see that throughout. But, you know, if that's a better way, do it the way I just showed you. Here, they're going to add the additive inverse of a negative 3 as a positive 3 to this side, positive 3 to that side. Instead of doing vertically, they're doing it horizontally. That's perfectly acceptable. So here this becomes 0, and we get x equals 10. And they do a check of it that we're not going to spend time on, because we've done some like that earlier. Now, what do you have to add here to get a positive 5 to become a 0? Well, a negative 5. So you could put a negative 5 underneath this, a negative 5 under this. This side becomes a negative 16. Our text is going to illustrate it horizontally. So you want to isolate the y by adding the additive inverse, or the opposite, to a positive 5. And there you get your 16. And you'll be doing these in your practice and in your certification. Now, for this one, let me work it out for you. We have x minus 2/5 equals 3/10. Now, another method I'm going to suggest, and this is a shortcut for how we do things like this. Now, what we're going to do to get this to become a 0 here is add here a positive 2/5. Well, a method that we use in later algebra is something that's called transposition, where we take a term from one side of the equation and just bring it over to the other side, and in so doing, just change its sign. So on this side it was a negative 2/5. Just physically move it over to the other side and change its sign. Now remember, the reason we can do this is to make this a 0, we added 2/5 to this side, which is what we're doing. This is just a shortcut. So now this 2/5 is gone, and we have it on that side. But in order to add fractions with unlike denominators, we have to convert this fraction. I'm looking for my pen here. That's good. To a denominator of 10. Now, we are allowed to multiply any term by a 1 without changing its value. And the form of 1 that I'm going to multiply this fraction by is something that will make this denominator a 10. So what do I have to multiply 5 by to make it a 10? And you're going to say 2. Well, then the form of 1 that I'm going to use here is 2/2. So now my fraction becomes 3/10 plus 4/10. And once I have common denominators, I just add my numerators, and I get x equals 7/10. So this one's a little more challenging. So as we see it worked out on the PowerPoint slides, we're taking the opposite of a negative 2/5, which is a positive 2/5. Here it becomes a 0, and on this side we have 2/5. But in order to add these fractions, I must make this 2/5 with a denominator of 10, so I multiply it by 1 in the form of 2/2. The key is, what do you have to multiply that denominator, 5, to make it a 10? So that's where I get my 2/2. They're not showing that in great detail. That was something that was done in Chapter 1 that we didn't cover that much. So I'm spending a little extra time. So we add our 3 and 4 together over our common denominator, and we get this. And if you put it in the original example, it works out and it checks. Okay, so here we now have to simplify a little bit by grouping like terms. And this is going to become a z here. And we group these together, and we've gotten that on that side. So now, what do we do with our 2/5 to make it a 0? Well, we're going to subtract 2/5 here, subtract 2/5 there. They're going to show it horizontally. Remember, we could have just transposed the 2/5 to the other side as a negative 2/5. That's a shortcut. But here they're showing it in some detail. And you get then z equals 1.5. And it does check. Alright, another form of equation is when you have your x term that's not a 1x. Here a is some value other than 1. So here we're going to use the multiplication or sometimes the division principle of an equality. So we're saying if we have a equals b and we multiply a by something, a c, and the b side by something, a c, it's still equal. It's not the same equation, but it still balances. So we're allowed to do that. Or if we divide a by c and b by c, it's not the same, but it's still equal. And again, what we want to do is hone down so that on one side we just have a 1x, or one letter, equal to some number value. And they're reminding us here that c cannot be a 0 because that would be undefined. Alright, and I'll show you what this is, which is they're saying they want something to become 1x. Again, we don't write the 1. And we would check it by, of course, substitution. Now, let me work this one out for you. The book does a very good job as well. So we have 5, and really this is 5 times x equals 20. Now, remember, 5 is the numerical coefficient of x, of the variable. We want this 5 to become a 1. Well, here's a case where we're going to do that by using division. If we divide this 5 by a 5, anything divided by itself is a 1. But again, if we divide this side, we must divide this side. So here the 5's cancel out. We get a 1 that we don't write. X equals 4. And 4 times 5 is 20. Again, this is the easiest type of example where you have this equals this. Now, there's another way to do it also, and this is something we didn't cover in chapter 1, where they do bring it up. And what can we multiply 5 by? It's going to be multiplied by something so that eventually it equals a 1. And the answer, some of you may recall this, is if we multiply any number by its reciprocal. That is, every number is over 1, we just don't write the 1. The reciprocal of 5 over 1 is 1 over 5. So if we multiply this side by 1 over 5, and we do this multiplication, here the 5's just cancel out, and we have 1 now equals 1. We had to introduce the reciprocal. So here they're showing us, theoretically, we could also do it that way. What is the reciprocal of 5? And that is 1/5. Now, notice here we're multiplying, but if we did this multiplication, can you see we would get 5 over 5, which is the same as dividing this by 5. So you could use the reciprocal, or the easier way, I think, is just to divide by the numerical coefficient of the variable, but you have to do both sides. So we'll see it done here. Here they're using the reciprocal of 5, both sides. There's the reciprocal. And you get 1x, that we don't write the 1, equals 4. And then the other way is we could divide by the numerical coefficient of the x, which is 5, and you get the same answer. It's a good tool to have, and the check works out. Okay, so here we need to combine like terms. We're going to get a 1.x and a 0.2x, 1.3x, and we do this subtraction here to combine like terms, we get a 9.1. Now, what would we have to divide 1.3 by to make it a 1? Think about it for a moment, and the answer is 1.3. So these then cancel out, give us a 1x, and then when we actually do the division here, we get x equals 7.0, and that checks out. And if we do the proof, it is true. All right, let me write this one out for you as well. Now, later we're going to have other ways to work with fractions, but here they want us to note that 4x over 5 is also can be written 4/5 x. And we want to sort of isolate the fraction as our numerical coefficient. So the question is, if we want a 1x here, what could we use to get any number to be equal to 1? And that same word again is its reciprocal. And the reciprocal is just flipping this over. This would be 5 over 4. But if you're going to multiply this side by 5 over 4, you have to do this side too. 5 over 4. So notice what happens here. The 5's cancel out. The 4's cancel out. And we're just left with a 1. 1 over 1 is 1. So there's our x. Now here we could do a little cross-canceling too. 5 goes into 5 once. 5 goes into 10 twice. So now we get 3 times 1 is 3. And 2 times 4 is 8. And our answer now is 3/8. Again, this was a technique of multiplying fractions that we passed over a little bit, so I'm taking a little extra time to show you this. The reciprocal, and then cross-canceling and multiplying fractions. And let's see what they show us here. So we're using the reciprocal on both sides, and they have factored the 10 here a little bit, so they're going to show us some canceling. So 1 times 3 is 3, and 4 times 2 is 8, 3/8, and that's what we had. And the check works as well. Okay, another one. Sometimes you'll end up with a negative x equals 4. But we don't want what negative x is. We want what positive x is. So what can I do to both sides to get this to be a positive? Well, if we multiply both sides by a negative 1, negative 1 times negative 1 makes this a positive 1. So, or if I divide both sides by a negative 1, here a negative 1 divided by a negative 1 gives me a positive 1x. Again, we don't write the 1. And then here, 4 divided by a negative 1 gives us a negative 4. So this checks out. Okay, a little application, and again, you're going to have many of these as we go through. A Blu-ray player was reduced by this much. The sales price was this. What was the original price? Well, we're going to say the original price is Y. Take away the discount. This gives us the price we pay at the register. So solving this equation, we're just going to add 45.50 to both sides. That will give us a positive Y. Here they're showing it in the traditional horizontal way. And you get the price is $211.40. Now, these are some practice problems. I see the tape is running a little long. You will be doing practice in your Hawks software program, but let's just do 4. Let's do the even examples here and see what we get. Well, I put all the answers up, but let's do number 4 together, because that's a little bit more challenging. What would be the reciprocal now, and I'll even change colors here, of 3/5? And if you said 5/3, you are correct. So 5/3. Here, these all cancel out, and you end up with Y. Here, the 3 will go into there once, 3 will go into there 11 times. 5 times 11 is 55. And then this one here with the fraction, I think, is good too. So this is 4/5 equals 3 over 1 here. Now, this one's a little tricky here. This is why I wanted to do this one for you. And I'm going to show you a technique we can often use to get rid of all the fractions like this. So we can multiply each term and there's one term on one side, one on the other, by a 5. In this case, the lowest common denominator is 5. And notice what happens. Here the 5 cancels out, and we're left here, I have room, 4 equals 15x. So I got rid of that tricky fraction because here we'd have to divide by a 3, and that was a little bit hard at this stage. So by getting rid of the fractions, we don't have to worry about that. So now we have 4 equals 15x. Now, how do we get rid of the 15 that's with the x? We just divide both sides by the 15. Here the 15s cancel out. I'm equal x equals 4/15, which is the answer. Okay, well, good luck, and this is running just about 30 minutes, so some of these may take a little longer than others, but hopefully you'll have some good notes for this.